Hello, students. Today we're going to talk about Le Chatelier's principle. And it is the idea that when you have a system in equilibrium, that if you add something to that system or remove something, in other words, disturb that equilibrium, that as long as the temperature is the same, it's going to try to shift either towards product, which is called to the right, or towards reactants, which would be to the left, to try to get back to equilibrium. So the system will respond by shifting in order to regain the equilibrium that it had previously. Now, this means it's going to maintain K equilibrium. It won't mean, though, that you have the exact concentrations or pressures you had before the disturbance, but the ratio would be the same. So what I want to do to give you a good, important example of this is to start off our discussion with a biological example, and then we'll head into the more traditional chemistry examples. Right now in your cells, CO2 gas is formed in your cells, and that's formed from the reaction of glucose plus oxygen to make CO2 and water. And the whole point of this is the cellular respiration is to make a high energy molecule called ATP. So in cellular respiration that occurs in your cell, in particular in biochemistry, we focus on muscle cells and brain cells as our main examples. But CO2 is formed and that's a waste product. So in the blood stream, CO2 reacts with water that's in the blood. So this will be in the tissues. If you want to think muscle cells or brain cells. And then in the tissues, the CO2 goes out of the cells, reacts with water in the blood, and forms carbonic acid. So do you remember that acid from Chem 200? And that is in an equilibrium, so I'm going to use the double arrows for that. Acids react with water to form hydronium ion. And in this case, monohydrogen carbonate, or what I call bicarbonate. And so if you notice, that's also in an equilibrium scenario. Okay, so what will happen in the tissues is that you're going to have a lot of CO2 because let's say you're running or jogging, you need muscle contraction for that. And so that's going to increase the demand for cellular respiration. And so what's going to happen is that there's going to be an increase in the partial pressure of CO2. Now, when we increase the pressure of CO2, that's adding a stress to the equilibrium that's here. So our K value, let's do Kc, concentration of carbonic acid over the concentration of CO2 is at a certain level. And by introducing carbon dioxide in here, that's a stress on that system. So the system's going to want to relieve that stress. And so when we add, in this case, a reactant, it's going to shift away from what's being added. So that's what Le Chatelier's principle will tell us. Is that if we add a reactant, it's going to shift to the right to consume it so that you can maintain Kc at the same value. Okay, now in the bloodstream, though, this is interesting because that's not the end of it. If you notice now, carbonic acid's involved in this second reaction that's linked. So as it shifted to the right, we do see an increase in carbonic acid, which now is going to cause a shift to the right in the second reaction. So now this is a reactant here, and that's going to shift to the right. Now this has some important implications then. And the implication that's important is that if you notice, that's going to make the amount of H3O plus increase. Now, we haven't done the chapter on acid base yet, but you did study acid bases in Chem 152. So what's going to be known here is that if you increase H3O plus, that's an increase in the acidity level. Okay, and what is also very interesting to note is that our acid level in our blood has to stay constant, fairly constant, because if it doesn't, then we can go into a coma and then ultimately die from that. So I know we haven't covered pH yet, but you've had that concept before. The pH in the body blood is at 7.4. Even slight fluctuations in this pH value can lead to trouble for us. We can have what's called acidosis, too much acid in the blood, and that can put us into a coma. Okay, so if you think about it, in theory, every time you run really hard and you have a huge demand for ATP because your muscles are contracting, that means you're going to increase the amount of CO2. And ultimately, because of Le Chatelier's principle, you're going to be increasing the acidity level in your blood. Now, the last time you went running, you did not go into a coma or die. You might have felt like it, but you didn't. And that's because there's something really interesting happens is that this blood ends up in the lungs. And in the lungs, we breathe out CO2. And that's the equivalent idea, is that we're removing a species that's involved in an equilibrium. When you remove a species, the Le Chateliers will say that it's going to shift to replace it because it wants to maintain the same K value. And so in the lungs, as we breathe out CO2, so this is coming out, then the reactions shift left. Okay, that's opposite of what we saw earlier where they shift to the right. So as in the lungs then, because these equations shift left, then this other one that's linked to it also shifts left. And what effect does this have is that we lower H3O plus levels. And so this means that that acid buildup gets removed. It gets removed by us breathing out CO2. And I love this example of Le Chatelier's because it really shows us how important Le Chatelier's is to everyday life as we walk around and we have a demand for muscle contraction. Our breathing helps to regulate our blood's acidity level, and it's all based on Le Chatelier's principle. Okay, now there can be things that happen that affect this equilibrium. You can have a disease, something going on in your body that even makes for a greater acidity level. And so our breathing's going to have to compensate for that. And sometimes it's not enough. And so there's going to be some secondary mechanisms that we'll talk about in the next chapter that kind of kick in here. Sometimes we ruin the system if we have a too much acidity level, which can happen in diseases like alcoholism. Then the body can't compensate through breathing alone. Okay. Another interesting little point here would be, let's say you're hyperventilating. So when you're hyperventilating, you're breathing too much CO2 out, and that's going to shift these all to the left in the lungs. That will lower H3O plus levels, but it can lower it too much, right? So we have to keep a balance in our bodies of the correct balance to maintain this pH at 7.4. And we're going to come back to this and bring in a lot more in the next chapter. But I just wanted to start us off with kind of an interesting example of Le Chatelier's. Bottom line, if you have a system in equilibrium, if you add a reactant, it's going to shift away from that reactant you've added. If you remove a species, any species in the reaction, that's part of the equilibrium. Le Chatelier says that you're going to shift towards that species to replace it. Okay. Ultimately, though, when the temperature is the same, all these shifts will allow us to maintain the same K. Okay, so let's go to kind of, this is the same thing I said. If you want to read this, you can pause me. But this is just the same idea, just written out, that if you have a reaction of A to B, if A increases, what's going to happen is you're going to shift this to the right to maintain the K. If you added B, so if you add B, then it's going to shift it back to the left. Okay, if you have a system in equilibrium, and if you decrease B, then it's going to shift towards it. If you decrease A, it's going to shift back, okay, to the left. So it will all depend on looking at the reaction and seeing who's being added, who's being removed. One important thing too, though, is that when we're talking about this, that the substance has to be part of the Q value or K. So if you add solids and liquids, which are pure substances that do not appear in the equilibrium expression, those have no effect. Okay, so let's practice one. I think that's the next one coming up. Oh, okay. Well, here's another, it's an example. So we have PCl3 plus Cl2 in an equilibrium to PCl5. Okay, if we increase the reactants, that is going to shift to the right. Okay, or another way we can get this to shift to the right is to decrease the amount of PCl5. Okay, if we want to shift it to the left, we would increase the amount of PCl5. So I'll go with red on that. So if we increase the amount of PCl5 or add PCl5, then it's going to shift to the left. And another way we can have it shift to the left is by removing Cl2 and PCl3. Okay. This is actually a great slide because this is trying to get you to understand that you're going to maintain the same K. So in this example, this is showing an original equilibrium scenario where you have at equilibrium 0.200 PCl3, 0.125, and 0.6. So take a second to figure out what the K equilibrium is for that scenario. And you can pause me. So for Kc, that's the concentration of PCl3 over, oh, that's a typo. This is PCl5. Sorry, that's a typo on that slide. Over the concentration of PCl3 and chlorine. Let me fix that weird looking 5. Oops, it's not letting me, huh? Okay, so we have our equilibrium expression set up. And with those values, that's 0.6 divided by 0.2 divided by 0.125. So go ahead and plug that into your calculators. I think it's 24. Okay, and what's going to happen is that that's our Kc. And so let's now say that we have a additional chlorine amount added. So now we're going to disturb or add a stress. So you see here in the chart, this has added a 0.075 of chlorine. So now we have a new amount of chlorine. And what Le Chatelier says is that this is going to shift away from that added stress. Okay, but there has to be a new equilibrium established, has to reach a new balance. And so from what we learned previous chapter, minus x plus x. But this new equilibrium still equals that 24. And we could solve for what that amount is, right? So this, I just wanted you to get a good feel for the idea that for sure the Kc value stays the same, regardless of the fact that we've added something, because the whole point is that Le Chatelier's principle says is you're going to maintain that constant. The only time you don't is if the temperature changes. Okay. Okay, so this is a kind of a more picture version of it. Trying to get you, if you like pictures more. I'm not a big fan of this particular slide, but it's showing us that we started off at a certain value for K. We added Cl2, so we messed it up, but it's okay because it's going to shift, and then you're going to maintain and get a new equilibrium, and you're going to end up back at the same K value. Okay, so let's practice a little bit. And I'll read this to you, and then you should pause me and try to figure it out. So you have your reaction, and we're going to say what happens if oxygen's added, what happens if H2S is removed, and what happens if sulfur is added. Okay, so let's go ahead and pause me and see if you can figure those out, and then I'll go through the answers with you. All right, so A is what happens if oxygen is added. If we add O2, we're going to shift to the right. And what happens to the amount of water? Well, if you're making more of it because it's shifting right, that's going to increase the concentration of H2O. Okay. All right, so maybe I can highlight with a different colored pen. So if it shifts right, you see an increase in the water. Okay, now this B says, what happens to H2S? Well, if it's shifted to the right when you add oxygen, then that means you're going to decrease the amount of H2S. Okay, so when it comes to this idea of shifting, it's really looking at reacting. Okay, see what happens to oxygen if H2S is removed. So if we're removing H2S, that goes out, then Le Chatelier says it's going to shift to replace it. So that's going to shift left. If it shifts left, what's going to happen to the amount of oxygen is that's going to increase. And then what happens to H2S if sulfur is added? Sulfur is not part of our equilibrium expression. right? Here, Q or K equals H2O squared over H2S squared times O2. So the sulfur as a solid's not included, so you have no change. Okay, nothing happens. Okay. All right. Let's talk a little bit about pressure and volume. When we talk about pressure, we're really looking at gas phase systems, those that have a gas. And you can think of the pressure as being proportional to the concentration. If you have a gas that's not part of the equilibrium expression, then it's not going to have an effect on it. Okay, so it has to be part of the equilibrium expression. And then let me show you, I'd rather do a actual question. So let's take a look at these and then we can go back to the written part. So let's say we have calcium carbonate solid. Okay, so let's think about some things that we learned from Chem 200, that if we decrease the pressure, I'm sorry, let me start again. Decrease the volume, so make the volume smaller, the pressure is going to go up. So this is in a container where we can adjust the volume. Well, if the volume decreases and the pressure starts to go up, the system's going to want to compensate for that. And it's going to go towards the side of the reaction where there's less moles of gas. So it's going to shift to the side with less moles of gas. Why? Because you want to try to alleviate that pressure. Okay, so decreasing the volume increases the pressure, and then it's going to shift to the side with the less moles of gas. Conversely, if we increase the volume, so a gas container expands, the pressure is going to go down, and it's going to shift to the side with more moles of gas. So looking at our first reaction, let's highlight something. We have no moles of gas on the reactant side and 1 mole of gas on the product side. And so what will happen is if we want to make more product here, increase the yield of the products as it's asking for, then we want it to shift to the right. So to shift to the right, that's a shift towards more moles of gas. And what that means is that you're going to have to increase the volume and decrease the pressure. Okay, so for more moles of gas, you would increase the volume so that you decrease the pressure, and then it'll shift to the side with more moles of gas. If you recall, pressure is proportional to moles of gas from PV equals nRT. Okay, so let's try the next one. Sulfur solid plus 3 fluorines to sulfur hexafluoride. Okay, so I'm going to switch the color of my pen. So in this case, you have 3 moles of gas total and 1 mole of gas. So if we want to, because it says increase the yield of product, we want this to shift towards the right to less moles of gas. And that means that we want a higher pressure, which is the result from decreasing the volume. Okay, and then C has 2 moles of gas on the reactant side and 2 moles of gas on the product. When they're the same amount, then this will not be able to be manipulated in this way. So in this case, it won't matter, and changing the volume and changing the pressure will not have an effect on that system. Okay, so you can read that. That's the written part, written explanation. Okay, our last section is regarding temperature effects on K. So when it comes to changing the temp, now we have a scenario where you will change K. So, but how you change K depends on one very important thing, which is whether or not the reaction is endo or exothermic. So an exothermic reaction, delta H is negative. So you had a little bit of this in your previous course. Endothermic reactions, delta H is greater than 0. So this here, we have to have information regarding a reaction to know how it's going to be affected by temperature. So let me give you an example. The combustion of nitrogen is very endothermic. Right now you have nitrogen buzzing around your head. It's not on fire. It's not reacting with oxygen. That's because it takes a lot of heat energy to burn it. I will ask you, what is it about nitrogen on a molecular level that would make it very difficult to burn? And if you recall from your Chem 100, it has that triple bond. So that makes it very difficult, very high activation energy. Okay, very endothermic too. So both. Okay, so now the thing is, though, is that we can improve the combustion of nitrogen by increasing the temperature. So in this case, what you want to picture is that if we raise the temp, we can picture this. It's not really a reactant, but the heat here, we could, if we write it, it just makes it easier to visualize. So if we raise the temp and add heat to this, then it's going to shift to the right. In the case of nitrogen, this is a reaction that goes on in a car, because in a car, the whole point is to burn octane, the hydrocarbon in the car, but the car brings in air, and the nitrogen in the air in that hot car engine, that provides heat to push and shift this reaction to the right. And so nitrogen that normally doesn't burn at room temp now shifts towards product. And you start ending up with NO, and that's a pollutant, and it keeps reacting. It can react with water to form an acid in acid rain. It can react with more oxygen to form other oxides of nitrogen. And this just creates a snowball of chemical changes that affect our environment, right? And recently with the fires, we've seen this so dramatically. So this is definitely Le Chatelier's principle, and it's shifting to the right. Now, in this case, you see an increase in K because it's not going to maintain that balance. And since you're shifting it to the right, you see an increase in product that increases Kc. Okay. In a reaction, where the reaction is endothermic, this one was endo. And in a reaction that's exothermic, Okay, what will happen is that when you increase the temperature and add heat to that system, then it shifts towards the left. Okay, and then what would happen there is that you see a decrease in Kc. The equilibrium constant is smaller. Okay, this slide is very important in industrial chemistry, as my interests are in biochemistry. Biochemistry is different because we don't change reactions in the body based on temp. We just don't, because our bodies are at constant temperatures unless we're sick. So this whole idea of manipulating temperature is definitely an industrial chemistry type idea, but I did give you an example of it here as an environmental discussion with these oxides of nitrogen. But if you think about it, if you were a chemical engineer, for example, and you were in charge of a chemical that you were trying to sell and that you had a product that you had to get out on the market, you would have to know this, right? Because your whole goal would be to maximize product. And so you would have to know, is that reaction endo or exothermic, and how you can maximize your product. Okay, and there's going to be an example here in just a minute of this idea. Okay, so we can practice some. So you have these reactions. I'll do the first one and then you can practice the other ones. How does an increase in temperature affect the equilibrium concentration and K? So let's do the first one. It's exothermic, heat releasing. So the easiest thing to do is to show it as a product. Yeah, it's not really, but it just makes it so much easier. So when it's exothermic, I'm going to write it on this side. And then increasing the temp, if I increase the temp, that's going to shift this backwards to the left. That's going to have the effect of lowering calcium hydroxide, and that is going to mean that K is going to be smaller. Okay. We can do B. You can pause me if you want to do that guy. Okay. If we add heat, increase the temp, that second one there is endothermic. You see how it's plus 178, right? Plus, so that means endo. If we add heat, this is going to shift to the right. CO2 will increase, and you'll see an increase in K. Okay. All right, let's wrap this up. You don't need to know this. So this is if you notice, it looks really similar to our Arrhenius equation. This is one that actually talks about the relationship between enthalpy and temp. So there is this equation that we could solve for what the new K is at a new temp. But this will not be on quiz. Okay, so I won't test you on that. And interestingly enough, with the idea of Le Chatelier's, a catalyst will speed up a reaction, but it won't affect the equilibrium position.